Welcome, everybody. Today is another special day. Yesterday, we had a very nice seminar related to the living matter cluster. Today, this is maybe more relevant to the packaging cluster that is at the interface between food science and fibers. So there are many members of the packaging cluster here. Can you raise your hand so that you see? Yes, that's the coordinator. And then there's Emily there. So packaging cluster, a new cluster in the university, funded for 2 years to incentivize networking. And the BioProducts Institute that I represent is part of that cluster as well. So welcome to those of you coming from the packaging cluster. Also welcome faculty from food science. Raise your hand. Yes, great. Food science, you see. And faculty and researchers from SALA, from architecture. Yes. So this is really great. This is the secret, multidisciplinarity. So with that very brief welcoming to you, I proceed with an acknowledgement, land acknowledgement, as we always do. Mohammad, this is a very special in this part of the world. We acknowledge the land where we work, where we learn. This is part of the territories of the Squamish, and we're very blessed to be in this area that is clean. And we then should preserve that clean air, that clean water, and the clean land. So, land acknowledgement. Now I proceed to introduce our speaker, Mohammad Peydayesh. We met some time ago in ETH. He's the right hand of Professor Rafael Mesenga. He's really a big figure in the area of food science and soft matter. And I also learned early on from Mohammad, very productive lecturer in ETH. When I came to ETH and my seminar, I wanted to show how many Nobel Prizes we have in UBC. Do you know how many? We have 8 Nobel Prizes. And I wanted to brag about it in ETH. But then I learned in ETH they have like 20 Nobel Prize winners. So I just stopped saying that. And then I shifted to gold medal winners in the Olympics. And I think UBC has a good number. So I try my best to promote UBC. But anyway, Mohammad has amazing papers in the area of sustainability, in the area of water. And he initiated with Professor Mesanga the area of amyloids, a lot of very good disruptive research in the area of protein assembly and amyloids structures. So we are very keen to learn from you, Mohammad, and you are warmly welcome. You have a big Iranian community here. I learned that Elena, Farhad are all friends, so this is great to know. And I hope that we can expand those networks that we have with ETH and all the colleagues around the world. So welcome. The floor is yours. We will have about an hour total, so maybe 40 or so minutes, and have plenty of discussion at the end. This crowd is very engaged. They will come up with many questions, so that's the best part. So I look forward to listening to that. So welcome.
Thank you very much, Orlando, for having me here and for the introduction. It's my pleasure to be here at UBC to present my work on protein nanofibrils for advanced material designs. So I would start with these top 10 global challenges for new millennium put together by Nobelist Richard Smalley. And we are not surprised to see energy, water, food, and environment on the top of this list. Indeed, if we consider these 4 together, all other challenges here somehow are related to these 4 elements. One way to look at them is to look at the cost of the feeding of the world today. At the moment that we are talking, 25% of global greenhouse gas emission comes from agriculture to produce food. 70% of our total freshwater resources is used in this sector to bring food to humans. 30% of global energy of the world to bring the food from farm to fork. And it is so sad to see 1/3 of all food produced for human beings is waste or lost. It accounts for around $1 trillion and is like the GDP of a country like Mexico. So it's huge. Food waste is of such significance that one of the targets of SDG 12, responsible consumption and production, is dedicated to it. This target indicates by 2030 we should have the amount of food waste that we produce. And it is clear that we should move from this linear economy of take, make, waste to a circular economy, that the waste could be considered as a source for materials production. In my research, I focus on agriculture and food waste to get the active building blocks, nano-building blocks that are available there, to use them to make some materials for addressing some of the global issues. In particular, I'm interested in proteins and polysaccharide fractions. So what we do, we recover these nano-building blocks from agriculture and food waste, and then we translate them to these soft materials by assembly of these nano-building blocks. There are different materials that mainly we are focusing on, is hydrogels, films, aerogels, and carbogels. And then we leverage these materials to address some of the environmental and energy issues worldwide. Like what? Like water purification, like using these materials for capturing CO2, to produce some energy materials, and of course the bioplastic for those of you that are from packaging sector. This concept itself resonates like sustainability. However, the way that we perform this valorization also should be sustainable. And because of this, always we perform life cycle assessment, we perform techno-economical analysis to be sure that the proposed scenario is sustainable and fits the circular economy criteria. So today mainly I talk about the proteins. There are many food industries that they produce side stream that contains protein. Here you can see the list of these kind of side stream from different industries. All in all, together they make around 1 gigaton per year. And each of these industry, they have like different amount of proteins and different types of proteins that here you can see on the right graph. Which basically, for example, feather, which is the byproduct or side stream of chicken industry, poultry industry, it contains keratin, and as you appreciate, like for feather, is around 90% keratin. So it's really rich in protein. Here you can see the whey that I think more or less you are familiar with. And then here we have the plant-based one. Depend on type of the protein, there are different processes to kind of recover this protein from side stream. So in this Sankey diagram, you can see like the side stream here, the methods that mainly used to recover this kind of proteins here. As you can see, enzymatic and alkaline ones are the most used one for recovering of the proteins. However, for example, in the case of whey, the membrane filtration, ultrafiltration is the main process to recover the proteins. So once we have these proteins, we can convert them to the protein nanofibrils or amyloid fibrils. And basically, these proteins are the core of my research. Means we recover the protein, we self-assemble it to these protein nanofibrils, and then with these protein nanofibrils, we make the materials. So the process is really simple. We need to go to first unfold the protein, and then let the protein to self-assemble to these long kind of mature fibrils. How? By heat treatment in acidic condition. So today, I'm gonna show you some of the materials that we make with these protein nanofibrils for mainly two applications: water purification and bioplastic production. So let's start with water purification. I think more or less all of you are aware of this issue of water scarcity and pollution worldwide. Means the water not only is scarce, but also we are contaminating it with really high rates. In this picture, basically you can see the main polluters of the water. Here we have agriculture, industry, mining, landfill, and then we have a wide range of pollutants that these sectors kind of introduce to our water resources. Based on the type of water, there are different technologies that we can apply to treat the water. However, here the challenge is not only that technology should be efficient, but should be cheap and sustainable. And here is the place that protein amyloid fibrils could help us. How? First, we can make different materials with them. We can make films, like we can make membranes with them. We can make hydrogel, aerogels as adsorbents, and even we can use them as a solution to purify water. These materials, we can apply them via different water purification technologies, like filtration, like adsorption, like distillation, and coagulation and fluctuation, which today I'm going to talk about these technologies. And by doing so, we are able to remove a wide range of pollutants from water, including heavy metals, including bacteria and viruses, PFAS, microplastic, and natural organic matters that we have. So just consider these membranes here, that on the surface we have the protein nanofibrils. There are different mechanisms in this removing of pollutants from water. So mainly, these protein nanofibrils are efficient for heavy metal removal. And for heavy metal, the mechanism is adsorption with chemical bonding, like with metal ligand chelation. However, in the case of organic pollutants, mainly hydrophobic interaction or electrostatic interaction, which later you will see play the role. And sometimes, in the case of silk nanofibrils, size exclusion, nanosieving is the main mechanism. So in this graph, you can see a wide range of heavy metals, actually, and radioactive compounds that we use amyloid fibrils membrane to remove them from water. As you appreciate, the removal efficiency for most of them is above 98%. And here you can see the surface of the filters after removing the metals. That gets the color of the metals that we remove from water. And the beauty of this technology is not only we are able to remove them from water, but also we can recover, in the case of precious metal, we can recover them to the elemental forms. Here you can see the nuggets of gold, platinum, and silver that we successfully recover from the wastewater that we receive. So once we make the protein nanofibrils, they are like in a dispersion, like cellulose nanofibrils that you make. And here is the microscopy image of them. You can see the characteristic features of them. Simply by screening the charge or by increasing the concentration, it is possible to convert them to the gel structure. Here is the hydrogel that simply by salt diffusion we made from the amyloid fibril solution. And then based on the way that you dry them, you can make cryogels that here you can see it here, or aerogel that here in this picture you can see. And then all these materials somehow can be used for different application. In one of the pioneering work, we use a piece of the cryogel, here for simplicity I just call it aerogel, to remove organic pollutants from water. And here you can see a piece of aerogel that we just added to dye, and within like couple of minutes all the dye get absorbed by the aerogel. And here is the pure aerogel from whey protein nanofibrils. In this video, you can see their performance for removing oil from water, and you can see within only 20 seconds, all the oil got absorbed by the aerogel. And then further, we applied for more difficult organic pollutants, like persistent, or some of them persistent organic pollutants, including pesticides, phenolic compounds, and pharmaceutical. Here you can see the model pollutants that we use. And in all cases, we observe really good absorption capacity, milligram per gram of the aerogel. So this study really showed that not only we can use the protein nanofibrils for heavy metal removal, but also for organic pollutants removal. Then we continue exploring working with this aerogel, and in this recent work from our lab, actually, we use food waste and e-waste to recover gold. So what we did, first, we get the whey from the food waste, we convert it to the protein nanofibrils, and then these protein nanofibrils, we just made this aerogel here, and then e-waste, we collected many motherboards and electrical waste, actually in university. We dissolved them in aqua regia, really a strong acidic solution. And then here we have like a soup of metals here. Copper, gold, platinum, iron. And then we place the aerogel in this soup of metals. And this aerogel selectively absorbs gold, which later with a simple heat treatment, we recover the gold. So these two graphs shows the performance of this aerogel towards gold. So here we have 8 metals, Au, Cu, nickel, Pb, Zn, Cr, Femn. And as you can see, the removal efficiency for gold is 93. Here, the goal is not to absorb all of them. Here, the goal is to selectively absorb the targeted metals that you are looking for. And this translates to this absorption capacity around 167 for gold, which is really excellent number for gold recovery. And then during this process, we realize if we put a piece of this aerogel in gold solution, as you can see here, in a gold solution with low concentration, not only we absorb them, but also we reduce them to the nanoparticles. This purple color is for nanoparticles of gold. Then we realize if we increase the concentration to like 1000 ppm of gold, we can go even to gold single crystal microplates without any treatment, just by absorbing them on the surface of aerogel and giving time. Here you can see the aerogel got really totally golden. And then this picture shows the nuggets that we recover from these 20 motherboards that we collected at ETH. And after analyzing it, we realized that this nugget contains 90.8% gold. And this translates to 21 to 22 carats, which was really amazing. This work really featured in many of news. Actually, it got really high scores in public kind of availability, like many news agency, BBC, World Economic Forum. And at the moment, this paper is one of the top 10 papers in advanced material, history of advanced material, with highest attention score. So far, whatever I just explained to you was with pure protein aerogels. But in one study, we just explore what will happen if we also add sugar to the formulation. So what we did in this story, so we had the whey protein here, we converted to amyloid fibril, and this time we add some sugar like glucose, saccharose, and this kind of sugars. And then we mix everything, and with hydrothermal synthesis at 180 for 5 hours, we realize when we open the autoclave, we get really nice carbon gel, which is a carbon, hydrothermally synthesized carbon, which later we dry to make this carbon aerogel. To just comparison, we kind of like remove this stage to make the amyloid fibrils, and we went directly from the native protein, we add the sugar here, and then we cook again to just compare how amyloid fibril formation affects the properties of the gel. So here is the results. On the top row, we have the one with the monomer, means protein was in this native form. And in bottom row, we have the one with amyloids. And here you can see the source of protein, which is whey, and here in this case soy, and different kind of sugar or polysaccharides that we use. And you can see like the ones with amyloid fibrils, they resulted in more homogeneous structures compared to the monomer ones here. The method is totally scalable, it's really simple. And here is the picture of carbon dots released from these aerogels, carbogels, let's call them. And then because we are talking about water purification, so we use a piece of this aerogel to remove pollutants from water. So here is the performance for some of the metals, especially the precious metal, and here is the removal for dyes that shows really acceptable and good performance for removing these pollutants from water. So let's move from the aerogel. Let's see what we can do with the solution of the protein nanofibrils. And here I'm going to talk about microplastic removal and natural organic matter removal. You know, there are really suspended particles in our water resources. And mainly they have a negatively charged. So if we manage to have something positively charged there, we can kind of have this binding between positively charged coagulant and negatively charged pollutant, and then they screen the charge, and with the gravity they can be sedimented. And in this application, we use another type of protein. Here we use lysozyme protein from white egg, and lysozyme has positive charge. So because of this, if you consider this microscopy image of latex microplastic in water, you can see it's like really homogeneous solution. After adding protein nanofibrils, the aggregation of them happens. You can see here the protein nanofibrils. And here is the water. Actually, we got the water from water treatment facility of City of Zurich. And after adding this protein nanofiber, you can see they start to be sedimented in the solution. Then we did the same, but this time for natural organic matter. Our model pollutant was humic acid. This picture, this image, shows the protein nanofibrils, their native one, without being in contact with the pollutants. And here you can see that they're covered by the natural organic matter. The aggregation of them happen. And again, here, the sedimentation of them there. So this was another application of the protein nanofibrils for coagulation and flocculation for microplastic and natural organic matter removals. And the last water technologies that today I want to talk is solar evaporation. You know, distillation is the simplest and oldest method for water purification, but it has always this problem of energy demand, or energy. It's an energy-intensive process. So what if we manage to supply this energy from sun to evaporate the water? And this is the concept for a solar evaporator. Basically, you have an object that floats on the water-air interface. On the top, you need to have a black kind of surface to absorb the maximum of irradiation of the sun. Here, you need to insulate the heat transfer to the bulk of solution to kind of confine energy here. And by confining energy, you can basically evaporate water. So what we did, we designed this kind of setup by using, again, here a monomer. We convert it to amyloid fibrils. And here we add like polydopamine to just make the surface black. And then we made these 2-layer aerogels that we used for removing salt. Because here the most interesting thing for us was to use this aerogel for desalination. So for this concept, basically you need unidirectional water pathways towards the surface of the aerogel. And in this SCM image, you can see like they're really well forged vertically, and these are our water passage inside the aerogel to have the continuous supply of water from the bulk to the top of the aerogel. In these pictures, basically you can see the temperature profile. So at the beginning, the temperature of bulk and the surface that aerogel is located there is like more or less same, room temperature, 20, 21 degree. After only 10 minutes, the surface temperature reached to 30 degree, which later, within 1 hour that we studied the evaporation, it increased to 32. And here in this simulation, you can see the confinement of the temperature within the aerogel structure. So we don't want to have the heat be transferred through the aerogel to the bulk of water. And by doing so, we managed to get 1.6 liter of water per square meter per hour with this aerogel, which is really good number because in 1 hour, 1 square meter of it can give 1.5 liter of water. So the other things is like the different condition. If we have 2 sun, like to give 2000 watt per square meter, what will happen? And then we had a chance to receive some water from Red Sea, from Egypt. And here you can see these 4 main cations available in seawater. And the concentration of Na just dropped from 10 power 4 to around 4, basically, which really shows like how this aerogel successfully removed the salts from water. At the end, we check the anti-fouling properties of this kind of evaporator. You know, once you evaporate the salty water, kind of salt stays there, the water evaporates. And after like some operation, you see the formation of these salt crystals on the surface of the evaporator. And like over the time, they make the surface white. So it's not anymore as efficient as before because it's not anymore black. So we realize if we stop irradiation, the light or the energy of sun to the surface of aerogel, this salt back diffuse again to the bulk due to the concentration difference between the concentration of salt on the surface of aerogel and the bulk. And again, after 1 hour, the surface of aerogel is ready for next operation. So this for real application, during the day, the aerogel can work, and during the night can be generated. As I said, always we check all technologies in terms of sustainability, and here I have the life cycle assessment for water purification technologies. Here we compare 3 kind of adsorbent. Here the functional unit for this life cycle assessment was to treat 1 cubic meter of lead fluted water with a concentration of 100 ppb. And we have activated carbon, we have tempo nanocellulose and protein nanofibrils. I just learned that tempo nanocellulose is not the best nanocellulose to include here. However, there was a study that I used the data of that study for running this life cycle assessment. And here we have 18 environmental impact. And as you appreciate, the protein nanofibrils results in the lowest environmental impact compared to these 2 other bio-based adsorbent. Like in particular, if you look at the energy demand that is needed to kind of produce this material with the amount that we want. And actually here we have the CO2 release of the process for treating this water by using these adsorbents. So life cycle assessment gave us the info related to environmental impact, but we know that sustainability has 3 pillars: techno-economic, environment, and social. So because of this, we ran this kind of analysis that not only we include the efficiencies, not only environmental friendliness, we include cost, stability, selectivity, simplicity, and public acceptability. And then we ran this kind of analysis, and we observed protein nanofibrils. They scored the highest compared to the other 2 adsorbents for this special and particular application. So let's move from water purification, and I want to talk about plastic production. You know, we are living basically in plastic era. The plastic production amount is like increase dramatically, and is expected by 2050 this amount even get doubled. So, and this plastic, most of them, they end up in environment. They are not biodegradable. They cause a lot of catastrophic impacts on planet. And one way to just solve this problem is to move from not biodegradable petroleum-based plastic to more biodegradable and more bio-based plastic. So in 2021, we actually patented a technology that we use proteins to produce plastics. And how we did this? So like always, we convert the protein to the fibrillar structure. Here we add plasticizer. The process was water-based. A biopolymer next to the protein. And then here you can see the plastic that we produce for different application. Actually, it was during the COVID time. Here is me with a mask. And this shows how like we can go from whey, which this whey can be from the food waste, to produce these transparent, flexible films that can be used for food packaging. Later, we had the chance to try other kind of side stream, food side stream, that here you can see canola cake. During production of canola oil, they press the canola seeds, and this leftover cake contains 30% protein. And then we get that waste, and we convert it to this kind of nice homogeneous plastic. We use okara and soy whey that are like the typical side stream of soy industry. Here you can see some of the application as a window for a food packaging. And then last year, Migros, actually Migros is the biggest supermarket in Switzerland, came to us and asked us as a proof of concept to convert 500 liters of their soy whey to sustainable packaging for their product, especially for their bread bags. And this soy whey is basically the water that comes out during the tofu production. And it is really acidic. At the moment, even it's not possible to give it to the pigs. So what they do, they consider it as a wastewater, and they have to treat this wastewater and then discharge it in the environment. So what we did, we convert this 500 liters of soy whey that contains soy protein in a really industrial scale, pilot to industrial scale, to these nice plastic films that later Migros used them in this setup, as you can see, to attach them to the paper to produce a bread bag, basically. And now we are talking with them to use these bread bags in one of the supermarkets in Zurich to see the feedback of their customers. So again, we did life cycle assessment, this time for producing 1 kg of the bioplastic. And here we had like PVF as a petroleum-based plastic, PLA, kind of really well-known bioplastic, and amyloid fibril bioplastic that again here, same as before, we observed the lowest environmental impact for the bioplastic made from the protein nanofibrils. So I'm not sure you are familiar with these planetary boundaries, 9 planetary boundaries put together by John Rockstrom, actually in 2009, I think, which shows which are like criteria, measures to show the health of planet for human beings. There are 9 planetary boundaries, but if we focus on climate change, which is basically the concentration of CO2, the safe boundary for human beings to live at this planet is 350 ppm of CO2. At the moment that we are talking, more or less is around 420 ppm. Actually, this is from 2021. At the moment is around 428 ppm. If we do the things as usual, by 2050, this number increases to 500 ppm. So now, just imagine a scenario on food waste that we consider 50% of this food waste to be reintroduced to the food chain, because in the hierarchy of the food waste, first you have to reintroduce it for as a food for human consumption. And with the other 50%, we convert the protein content to the bioplastic. By doing so, we can decrease this projected amount for CO2 by 16%. Of course, it's not enough to bring the CO2 level to the safe boundary or below, like the current condition. However, this 16% itself, by knowing the fact that it's only about food waste, is a significant number. So I talk a lot about water purification. I talk a lot about plastic production. At the end, I want to show you another application of these protein nanofibrils. And because I know in BioProduct Institute, you are a powerhouse in polysaccharides, I just want to show you what will happen if we mix these protein nanofibrils with polysaccharides. And in this case, I chose a hyaluronic acid because it's a long chain, negatively charged polysaccharide. And what we did in this work, we let the protein fibrils at acidic condition, positively charged, to be in contact with negatively charged polysaccharide. And based on the way that you let them to be in contact to each other, you can produce different materials, basically the interface between them. So if you put them on the top of each other, you make this film. If you inject one in the other one, you make the capsules. And if you inject and try to remove the interface, you can make the fibers. And then later you see with this conservation process, which is an electrostatic actually interaction between the nanobuilding blocks, we made these kind of films, which you can see they are really flexible. They're different from the protein, pure protein films, because pure protein films, you need plasticizer, you need other compounds, but this one is only made from HA and protein nanofibrils. HA is hyaluronic acid. So here you can see the capsules that here in this case we inject protein nanofibrils in a hyaluronic acid solution. And here you see the fiber that we are spinning out from the solution. Here it was around 20 microliter of protein nanofibril inside the hyaluronic acid. And you can see, you can spin it out 1.2 meter from only this 20 microliter of protein nanofibrils. Later, what we did, we just dried some of these capsules and we used them for treatment of ulcer via international collaboration that we did with a Brazilian group in Sao Paulo. So they used them for treat the animal, actually, and here you can see the result. So here is the lesion area based on these images here. And here is omeprazole, the drug that now is being used for treating the ulcer. And here is the coacervate that we made with mixing protein nanofibrils and hyaluronic acid, which shows even we can go more than environmental application towards the therapeutic application. At the end, I would like to thank all my collaborators at the Laboratory of Food and Soft Materials at ETH Zurich, especially Professor Metzenga, but also all my students and collaborators from different university and institutes in the world. And by this, I finish my talk, actually. Thank you very much. And I would be happy if you have any question to answer them. Thank you.
Thank you, Mohammad. Beautiful presentation, amazing illustrations, and the content was amazing. I think this is alchemia. This is not chemistry. This is not chemical engineering. This is alchemia. I have many questions. Maybe we can give the chance to the audience to ask. Yes, I will be passing the microphones. Here, there.
Thank you, Dr. Peydayesh, for the presentation. I was amazed by the number that you introduced in the beginning about $1 trillion in the economy being wasted. Has there been any analysis done to see what would be the capital expense, operational expense, or even the transition expense from the current traditional method to the perspective that you just announced? Because I'm thinking if we want to apply it worldwide, has there been any analysis done to see the feasibility of that transition? Yes. Thank you.
Thank you very much. Actually, there are different side streams in food industry, and there are like wide range of application that you can do, like the innovation that you want to do with that. If I want to talk about the protein nanofibrils, basically you need like to have an acidic condition and heating, so you need some energy for that. But always we include this energy in our life cycle assessment and techno-economic analysis that we do. And then at the end, it really depends on the product that you introduce or produce. You know, that one also has value. So unfortunately, worldwide, there is no like a kind of single study that shows if you use protein nanofibril for this kind of application, how much going to be like the cost or the efficiency or whatever. However, like in some of our paper, we include this analysis. That, okay, the protein, this is the price for recovery, this is the price of the product compared to the competitive products in the market. And always the goal is to be in the range of other product, maximum like the tolerance of 10 to 20%. Yes.
Question here.
Hi, Professor Mohammad. Amazing presentation. I had a question about the water evaporation technology. So you said that you were able to see the channels which were going perpendicular to the water surface. So how do you control the orientation of those channels? Because if you want to do something in commercial technology, it's very hard. So I was curious about that part.
Yes. Thank you very much for this good question. Actually, in our lab, the way that we tailor this kind of vertical channels was with freezing the gel from the bottom towards the top. So what we did, we didn't put the gel inside like the freezer. What we did, we had like a surface that was cold, and then the ice crystal grows from the bottom to the top, and by doing this, we managed to have this channel. In industry, of course, it needs a process to be developed to kind of unidirectionally freeze the water inside the gel towards the top. However, in lab, we just did it by like having a cold surface and putting the gel there and let the ice crystal grow towards up. Yeah.
Question here. Then we go with a scope. Then here.
Hi, so my name is Thanos. This is actually a topic near and dear to my heart. I've actually done a lot of work on recombinant protein, essentially amyloidogenic proteins. So it's actually kind of funny to see kind of a bit of the same results, especially like heavy metals, these kinds of things. My question was more along the fibrils and film sortifying. So when you're actually forming these films, like is that essentially... are you forcing alignment through things like vacuum filtration? Are you pressing it down? How exactly are you actually generating these films?
You mean the films as a bioplastic or the films for membranes?
The bioplastics.
So, yeah. So the bioplastic was with a simple solvent casting process. So we didn't align the protein nanofibrils because we didn't really want them to be aligned. So what we did, we had like the the protein nanofibril solution. We add a plasticizer, in some cases a biopolymers, and then we just pour the solution on a substrate and we dry the solution. So the alignment of the fibril might be alignment there because of the surface and the air, kind of, but we never seen this alignment inside the film, kind of. However, there are many applications that if you manage to align them, kind of, like imagine the part in contact with the substrate, they are aligned like in parallel, but on the top you have like a kind of mix structure. You can have kind of actuators. So is another topic, like it goes to responsive materials more, that you need like this kind of anisotropy in the system. However, for simple bioplastic, no, the alignment, we didn't care about it. And yeah, just simply by solvent casting.
Thank you.
So maybe piggybacking on that one, so there is also the work of Thomas Knowles. He was using soy proteins. That makes a lot of sense because these are the cheapest, right? Yes. Protein isolates, soy isolates, soy flour. Yes. These are very cost competitive. So how do you differentiate from that very recent work using soy proteins to make bioplastics?
Yes. So yeah, actually really good question. It really depends on application. So in the case of bioplastic, of course, you should go with the proteins that are cheap. Why? Because it's really tough market. Plastics are cheap. You have to compete with them. So because of this, soy, like per kg is $1 to $2 compared to whey, which is like the isolate one is around 10 to 12. So of course you have to go there. But now, even we don't want to use the soy protein. We want to use waste. And the study that I just showed to you, soy whey, is like really waste. And the goal was to not treat it, to not recover protein, just convert it to the plastic, which we did successfully. Thank you.
Scott?
Yeah.
It was a very nice presentation. I had a colleague collaborator at Virginia Tech, and every time I'd walk into his lab, he worked a lot with proteins and self-assembly. He'd do a lot of hydrolyze all these different proteins. His lab stunk from all these proteins that were hydrolyzed. And then if he was to do any like milk processing, like if he's using keratin, like it almost smelled like fried chicken. And so can you comment on, like, your properties look great, but those other properties, like kind of any odor or any type of those especially important for, I think, bioplastics. Mm-hmm. And is there any a way to kind of get around those?
Mm-hmm. Yeah. So basically, again, it really depends on the type of protein. If you go with the whey, for example, soy whey that we use, it has some smell. It's not a bad smell, but it's like kind of soy smell. I don't know how to explain the smell, but it is there always. But if you go with whey, the isolate one, like the pure protein, there is no smell. There is nothing. There is transparent. In the case of canola that I just showed to you, there is no smell, but there is color. It is brown color. So many customers, they don't want to have that. So it really depends on application. Sometimes even you can have them as a food, kind of. Like imagine this bouillon cube that you make soup with them, that you just wrap it with a protein, for example. So your comment is valid, is correct. Sometimes we see like some unwanted properties, but it really depends, and we can kind of fix them based on the application.
You were talking about Justin Baron? Yes. Oh, I got it.
Thank you so much. Thank you so much, dear Professor Orlando, and thank you so much, dear Mohammad. Have you checked your amyloid fiber for CO2 reduction as a catalyst before?
So as a catalyst, we did some works on CO2 capture with protein nanofibrils. We use protein nanofibrils to make an aerogel. We observed that they don't have really good adsorption capacity for CO2. However, they're made of this amino acid. You can use them for biomineralization. You can have a nanoparticle being kind of attached to them, and then by doing so, you can make a catalyst, or you can use them for direct CO2 capture. We have 2 papers on CO2 capture, but mainly hybridizing protein nanofibrils with some active CO2 adsorbers, not purely protein nanofibrils. So adsorption capacity, I think the one that we work with was with MOF. So we mix UIO66 with protein nanofibril to make an aerogel. And if I can recall correctly, it was around 1 mole or millimole, you can correct me, millimole, 1 millimole per gram of the aerogel. The best performance that we get. Yes.
Presentation. My question is about the surface chemistry of these nanofibrils that you're taking from the proteins. How easy it is to, for example, decorating it with carboxylic or amine functional groups, and have you studied the interfacial activity of these nanofibrils to all searchable self-assembled constructs?
What are those constructs? Sorry?
There are a kind of a structure formed through interfacial complexation. For example, you have nanofibrils with carboxylic acid functional groups or even amine. They interact with the negatively or positively charged depending on their surface chemistry, and they could either be dispersed in solvent, immiscible, or even miscible with each other.
Can I comment? So what he's saying, I translate. What he's saying is that you can do pretty much what you showed today with nanocellulose, nanochitin. You bring there the negative and positive charges, and that's the beauty of proteins. You have amphoteric behavior, right?
Yes.
So to some extent, we can do many things like this using more pure streams from plants, right?
Yes.
So in a way, also adding my question, what is that advantage that you have? Because you were using tempo nanocellulose, right, to compare. But if we broaden this a little bit more to plant polysaccharides and polyphenols, tannins and all this, lignin, you had there a very rich stream of compounds that can be very competitive. So more or less related. So if you can expand, that would be great.
Yes. So basically, they are really functional because they are amino acid, and amino acid is functional units there. For CO2 capture application, we try to put functional amine groups on this, and we successfully did it. In the case of mixing them, hybridizing them with other material, I just showed to you HA1, hyaluronic acid. In one of the studies that we recently actually performed, if we have time quickly, I can show it to you. We mixed them with chitin nanofibril, which by the time that you were in Zurich, I briefly talked about it with you, but now the paper is published. But I can show it to you, basically, if I have it here. Yes. So here is the process that we did, basically. So we get the fibers from the chitin, from the shrimps and crustaceans. And here, again, the self-assembly of them to make the amyloid fibrils. And then we mix them. And here, again, as Orlando said, positive, negative charge plays the role. And then again, here, even we went further. We added like iron to make the magnetic hydrogel. So it's always fascinating to mix them with other kind of building blocks, especially the polysaccharide one. Because once we make them, they are really acidic and positively charged. And if somehow you manage to control the way that you mix them together, you will be able to make really nice materials. Yeah.
Farhad will be asking something about MOF. I can bet you.
So you already lost. So thank you, Mohammad. I have some question about the adsorption performance of your sample. So I would say the main mechanism here in adsorption is some chemical ones. So you will have the problem about the regeneration of your sample. Another question is that, let me ask the question.
Yes.
So I think my understanding is that this type of adsorbent is good for adsorption, not for membrane filtration. So, and I have another question which is related. How is the stability of your sample in harsh basic media? Is it okay?
Thank you very much. I think the first one was about the regeneration of them, right? It really depends. In the case of metals, yes, I agree with you. So you don't get really good regeneration. However, in the case of organics, the study that I just showed to you, we just learned that by acid washing the aerogel, even you can increase the absorption performance. In the case of your second question related to there might be better for absorption than membranes, the mechanism is absorption. This we know. There is a startup from our lab named Blue Act that, for absorption, sometimes you want to have the dynamic absorption, means just water comes and goes out. And because of this startup produces membranes. And by talking about membranes, I don't mean like the membranes, molecular, like sieving or filtration. No, it's a bed that the water comes and is absorption that takes place really fast. So yes, the mechanism is absorption, but there is still membranes that you can make. Let's call them adsorptive membranes. And the third question, I forgot. The stability, yes. The stability. Always when you have them in acidic condition, you get the best performance. Like the results that I showed to you, especially if you work with the metals, the concentration, if it's high, the solution is acidic. So it's perfect for you. However, if you go to basic, the efficiency decrease. They are not really good. They don't like the basic conditions. Yeah, but luckily, like many of the side stream or like the wastewater, they have acidic condition. Yeah.
Professor Cranston here?
Yes.
Thank you so much for sharing your beautiful work and for the efforts to quantify sustainability. It's really challenging, and some of us don't do it, but it was great to see your results. I was thinking when we did nanocellulose aerogels a way back, and we were showing that they could absorb 60 times their own mass of oil. That was great, but as soon as they came in contact with water, they liked water more, so they would kick out the oil and take up the water and then sink to the bottom. Do you have similar problems where your materials prefer one over the other, and that might cause challenges in a scale-up? Like trying to use it for oil spill cleanup, for example.
Yes. For us, it's really important to see you put them in contact with which phase first.
First, yeah, so
because
order
they're
matters.
amphiphilic, the protein nanofibrils. So cellulose nanofibril, maybe they really like water, but proteins, if they become in contact with oil, they don't show the same behavior as you just said. So they are like, they like oil only.
Okay.
There is a paper that we show actually with the videos that if you put first oil, then the membranes made of the protein nanofibril really just pass or permeate oil. But if you put first water, only water, so oil doesn't work.
Excellent. And I know we're out of time, but I really have an important why question. I want to know why it absorbs gold preferentially so well. But maybe if it's too long an answer, we can talk about it after.
So,
but why?
I can answer this question more experimentally so it's all about kinetics, the reaction, the chelation, reaction, the kinetic of this reaction, that we know that for gold, we have it faster. But as a rule of thumb, usually the heavier the metal, the better the performance. So with the sodium, with calcium, we never seen like really good absorption capacity. But with heavier metal, with lead, with gold, we observe really better performance. But in the case that we have all of them in the solution and they're like is a soup, it's all about kinetics. And I can say that, yeah, the kinetics toward gold is faster. That gold goes quickly, saturate the active binding site, and there is no anymore active binding site for lead.
I have many questions, but I was in the back and Tianyu told me to ask you one question. She's working on packaging. And one of the big things in packaging is heat sealability, heat sealing. What about that with these protein materials?
They are.
Okay, that's great. That's great.
Okay.
Super. Yeah. I think this is all for today. Thank you very much, Mohammad. Let's give him a warm applause.
Thank you very much.
It's wonderful to see what BPI has organized this week and will continue to do. The attendance is amazing. The engagement is amazing. I'm very excited to see this. Yeah. We have a number of clusters in this area. And this week alone, we have already one talk yesterday with two colleagues related to mycelium, very interesting. And on Friday, we are going to have two more talks, one on lignin and the second one on carbon materials. So please come on Friday at the same time. We will have also sandwiches, so this is also a good magnet. But above all, I think this is amazing, the questions and the learning opportunity that we have. So thank you very much for visiting us. Thank you.
Thank you, guys.